Hi, thanks for checking out our work on predicting long horizon futures by conditioning on geometry and time. Our work explores the task of generating future observations given the past. Traditionally, this task has been widely studied in the form of video prediction or video generation using the RGB frames of a video. Since learning at scale remains computationally expensive for video generation, we explore more invariant modalities like pseudo-depth, which are 1. Easily available with present-day monocular depth estimators, and 2. Easier to learn from. Depth is also directly usable by downstream robotics applications. Since the future is inherently multimodal, we use diffusion models to predict multiple diverse future geometries for a given dynamic scene. The key insight of our work is that one can lean on the explosive advancements in image diffusion models and use them for video prediction. This is because the data that these models are trained on likely covers the space of all temporal events or actions. To this end, we develop our architecture on top of the recent Stable Diffusion Image Variations model, which uses the clip image embedding as the conditioning in the diffusion unit. Similar to 0, 1, 2, 3, we additionally concatenate the conditioning image with the input noise. To support multi-frame conditioning, we simply concatenate the sequence of images and their embeddings. We also add a control knob to the diffusion model in the form of input and output timestamps. Intuitively, the timestamps allow the diffusion model to link the given images together and understand their temporal relation. The timestamps are positionally encoded and concatenated with the clip embeddings. While at inference we use this model to forecast a single time step into the future, we interestingly find that training the model to predict random timestamps results in a better forecasting performance. Now at inference, in order to forecast, say, 10 seconds into the future, we could either directly jump to this future timestamp, or we could take multiple inference pathways to reach this future timestamp. In our work, we find that a linear combination of two different inference pathways gives the best forecasts. We call this mixed sampling. Mixed sampling is a linear combination between autoregressive and direct sampling, and so we find that it is able to generate temporally coherent predictions like autoregressive sampling and more accurate predictions like direct sampling. Using mixed sampling, we are able to generate plausible and diverse futures for in-the-wild scenes for any horizon in the future. We also evaluate shorter forecasting horizons, specifically 1 second into the future, and show qualitative and quantitative comparisons with 3 state-of-the-art approaches and other more simple baselines. Given the same amount of training resources, we find that it is much harder to train our video prediction model for RGB forecasting and much easier to train it for more invariant quantities like depth and luminance. Thank you for listening. For more results, please refer to our main paper and supplementary material.